Hello, welcome to the talk. This is Minghua Chen. I'm currently a professor at School of Data Science, the City University of Hong Kong. This is a joint work with my student Qiulin Lin and Wenjie Xu at CUHK and Xiaojun Lin from Purdue University. Today, I'm going to talk about a probabilistic approach for demand-aware ride-sharing optimization. So the scenario we'll consider is dynamic ride-sharing. In my understanding, it is a ride-hailing service that provides transportation service to anyone, anytime, anywhere with ride-sharing feature. That means multiple passengers with a similar itinerary and schedule can share the ride together. And ride-sharing is a multi-win paradigm. For the driver, it's more lucrative. For rider, it's more cost-effective. For the transportation network company like Uber or Didi, they can increase their service capacity. And for the transportation system, this is a good news as well, because by sharing the rides together, there is less congestion and less pollution, because there will be less vehicles on the road while serving the same number of passengers. Indeed, the study in Manhattan shows that the 98% of the rides currently in Manhattan can be served by 1/3 of the fleet size, and if we allow a ride-sharing capacity of 4. Okay, but to realize these benefits for multiple parties is non-trivial. In particular, the critical challenge in ride-sharing is the joint request to vehicle allocation and routing. So request to vehicle allocation means given a set of requests and the existing distribution of the vehicles, how you should map the request to vehicles. Okay. And the ride-sharing routing means once you have picked up more than one passengers, how to deliver them to their destination on time and with a minimum cost. And indeed, one can easily see these two issues are coupled together because the outcome of one module is actually the input to the second module. Conventionally, the problem was solved in a demand-oblivious manner. That means when the vehicle picks up the first passenger, he will follow the shortest path to the destination. And when there is a second request appear, then we'll take the detour to pick up the second passenger. Okay. Recently, there has been a demand-aware approach that is trying to take the demand statistic into account when perform the routing for the first passenger. So in this way, hopefully you don't, when the second request appear, the vehicle does not need to take a lot of detour to pick up the second customer, and thus reducing the overall cost and the delay for passengers. In this work, we're going to focus on this demand-aware setting and try to understand the answer to the problem. That is, given this demand statistic, how you should jointly optimize the request to vehicle allocation and the routing so as to maximize the TNC throughputs. TNC is just the transportation network company, like Didi and Uber. Okay. It is a critical challenge, so it has been studied to some extent. In the literature, there have been multiple works try to study this problem, but only for special cases. In practice, Uber is taking a decision tree-based heuristic approach. That means the vehicles try to make their decision more or less independently. And in our work, we try to consider the demand-aware setting and the ride-sharing, and also try to do the fleet-level optimization. In particular, we made the following 3 contributions. The first one, which I think perhaps is most interesting one, is that we develop a probabilistic framework that allowed us to study demand-aware ride-sharing optimization. Okay, and then the key insight there is that we should view these pickup opportunities as a system resource and try to allocate the system resource to individual vehicles so that the total system performance is maximized. Okay, so by taking this view, the ride-sharing problem is essentially a resource allocation problem. And then we develop a decentralized algorithm and for this pickup maximization problem, which happens to be NP hard, and we have to achieve a certain performance guarantee under certain conditions. And we carry out simulation based on real-world chases and show that our algorithm achieve up to 46% more pickups as compared to a demand oblivious approach. That is the high-level one-slide overview of our contribution. And next, I'll try to dive into the details to explain our framework and our solutions. Okay. First, we model the transportation network. In particular, the transportation network is modeled as a directed graph. But for our purpose, we focus on a region graph instead of directly on the transportation graph. The region graph is try to chop the entire transportation network into multiple individual regions. Within each region, the nodes can reach each other within 5 minutes. This communication time. Okay, and then we'll at each edge then represent the fastest path between two regional centers. Okay, and this region is how we model the passenger and vehicle pickup relationship. And in particular, only the vehicles within the same region as riders can pick up the rider, so that when the driver raises a request, he or she either get picked up within 5 minutes, or you will be this request will be gone otherwise. Okay. For our work, we focus on the region graph. Okay. And how do we model the demand as a source, destination, and time tuple? And we set the waiting time to be 5 minutes, and the deadline for the vehicles to serve this to transport this passenger is alpha, is a number constant larger than 1, multiply for the time used for the shortest path. For instance, alpha equals to 1.3. That means you can tolerate 30% more time than the shortest path. And for the demand-aware setting, we assume the demand statistic is given. We know for SDT, this particular request, what is its probability there will be let's say two riders coming from S to D at a particular time t. Okay, we assume this is given. You can learn this from historical data or doing machine learning prediction. Or you can use some of the reservation from the user as well. And with that, we come to this demand-aware ride-sharing optimization. We in this problem setting, we have n vehicles, in this case 3. Each at most has 2 seats. Okay, so you can sit 2 riders. And they are already serving the first rider, and then can pick up 1 more rider along their way. And the objective is that given the demand statistic, how to do the assignment, allocation, and as well as the routing, so that you maximize the expected pickup for the system. Our idea is to treat this pickup opportunity as resource. Okay. In particular, the system, we view this probability for the riders to appear as resource and allocate this probability across vehicles. Take the first vehicle as an example. system can allocate the following system resource to the vehicle. That means the entire region graph, as well as the probability for this vehicle to pick up a passenger at certain node. Okay, so you can allocate this as a probability. Okay, and the vehicle, once they observe this pickup opportunity, you can then try to make your own decision, try to maximize your expected pickup. Okay, so by doing so, we envision then the system throughput can be maximized. More formally, we define a probability. Here is y for one for each vehicle and for a particular it is a demand. Okay, for instance, this y, this green green y, it means that is the pickup probability. The probability that this green vehicle will be able to pick up with one request, and the events their riders appears from the node at the node 6 to node 7 here. So this is the probability. So you can assign this define this probability for other two vehicles as well. So then it turns out these probabilities is feasible if only if they satisfy the linear inequalities. So these linear inequalities are more or less pretty intuitive. It just says you cannot be larger than this resource. What you allocate to you, it cannot be larger than what's available in the system resource. And the second set of inequality says that on average, the number of passengers that pick up should not be more than what the number of pickups should not be more than the number of passengers. Okay, so this is the two set of equality. This necessary sufficient condition, and the user once you give the routing, give the potential like the pickup opportunities, then they will do the routing so as to maximize their number of pickups. In this case, it's just maximize the probability of picking one customer along the way. Okay, so it's just 1 minus the probability that you cannot pick up any customer along the way along the node, along the path. And this is a non-convex problem. Okay, this like the objective is non-convex. So the first step we do is to approximate this non-convex function with a linear function. And indeed has an approximation guarantee. Okay, and then with this in mind, then we formulate the demand-aware ride-sharing problem as a linear integer problem. That we try to optimize allocation decision and the routing decision so as to maximize the approximate total number of pickups. And the constraint involves this allocation constraint and also this vehicle to region balance constraint. Okay, and one thing there's a structural insight is that if we can relax this constraint, then this allocation and the routing problem are decoupled. Then we follow this idea, we can develop a dual subgradient algorithm for in each iteration. We first system will optimize the pickup opportunity allocation across vehicles. Okay, so it's just this is what system is observing that will allocate the pickup opportunity to individual vehicles. For instance, in this case, the first vehicle. And then for the vehicles, individual vehicles, they are optimized their own routing and given the so-called heat maps they observe. Okay, So with this, they will then this is what they're doing in each iteration, and you repeat after until convergence. Indeed, the algorithm will converge. Okay, and the conversion rate is 1 of square root of k, which is standard for dual subgradient algorithm. And what's interesting is that although the original problem is NP hard, but if you run this subgradient algorithm, and if a complementary slackness condition is satisfied, then this algorithm upon convergence will give you a 1 minus 1 of the approximation to the original NP hard problem. Okay, and this is some of the interesting performance guarantee. In practice, once the algorithm terminates from the algorithm output, what we get is the a route for each vehicle to deliver the first rider. And on the way, if at a certain time a second rider appears, then the system will do the allocation, then and allocate the users to the vehicles in the same region. And then those vehicles who pick up a new customer will follow a demand-aware, do a ride-sharing routing. Okay, and so the system will also re-optimize whenever there is a change in the vehicle states, then to pursue the long-term to optimize the long-term performance. Okay, and so that is so our design and our solution, our algorithm, and the next is we try to see how well they perform. We collect the 6 months data from New York City and more than 50 million trips data. And from the data, we learn the demand statistics, and we pick up source and destination pairs and carry out 100-day evaluation. Okay, so there is some result I'd like to share. First result is saying by doing doing demand-aware design, you can get substantial performance improvement than the demand oblivious approach. In here we plot the number of pickups for the at different time of the day and for 3 different schemes. The red one is the demand oblivious one, just do the shortest path routing and greedy reroute. Okay, and the blue one is our proposed approach. That is a joint allocation and the routing. Okay, the green one is something interesting. Is the individual vehicle see the same like the heat map and try to do the optimization independently. So they don't coordinate to optimize the overall system performance. Okay, as one will observe here is that our algorithm's performance is 46% better than the demand oblivious approach, and about 20% better than the independent routing approach. Okay, and further we also explore how the empirical pickup performance change as the number of vehicles, like the fleet size. What we observe is that when the number of vehicles is small, then 3 schemes have more or less the same performance. This is because in this regime, the performance is mainly limited by the fleet size. It doesn't matter whether or not you are using some intelligent this ride-sharing optimization or not, doing ride-sharing optimization or not, you'll get the same performance anyway. On the other hand, if you have a lot of vehicles, then it's really important to carefully balance the vehicles across different regions, and And so in this case, the pickup efficiency will kick in. And if some scheme can do well in balancing the vehicles across the region, then they can observe a larger number of pickups. Okay. And the last one I want to show is in ride-sharing service, usually the user is charged less, but at the cost of at the expense of need to perhaps like sit in the car for longer amount of time to reach their destination. So in here, we model this as a delay tolerance factor. And we evaluate how the pickups change as a function of delays tolerance factor. What you show here is that if we allow 60% extra trip time, then essentially this allows the ride sharing to double the throughput. What does that mean is that essentially you can serve almost twice as much of the passenger, use the same number of vehicles. Okay. So hopefully this gives you some of the practical insights. Let's try to conclude here. We introduce a probabilistic framework for demand-aware ride-sharing optimization, with the key idea of treating the pickup opportunity as a resource and allocate the resource to individual vehicles, and then individual vehicles try to optimize their own pickup performance. Okay. So the pickup opportunity is allocated in a way so that you try to low balance the vehicles across different regions, so that to improve the overall system performance. And we developed a decentralized algorithm for the TNC throughput maximization problem with certain performance guarantee. And the simulation shows that the demand-aware approach can achieve much better performance as compared to the demand-oblivious approach. There is some there are a lot of future interesting future directions. For instance, can you have better algorithms with better performance guarantee, and can you maybe we can try to maximize other objectives rather than just like the expected throughput, just like the throughput. That maybe we can take the fairness into account so that the vehicles get their fair share of the system performance, of the system benefit, so on and so forth. Okay, with that, I conclude my talk, and thank you very much.